We've been talking about equilibrium, and we learned how to write equilibrium constants based on the concentration. We can also use pressure instead of concentration. For a gaseous reaction, the partial pressure of each gas is proportional to its concentration. Can't remember if I'm supposed to write anything in there or not. I'm going to write something in there. This feels like a red kind of a day. Remember Pivnert, ideal gas law? Well, N is in moles, volume is in liters. That's molarity, right? So the molarity of a gas is proportional to its partial pressure. And then these two things are constant. So we can use partial pressures instead of concentrations. So Kc is equilibrium constant with respect to concentration. And so that would be molarities of the different gases. Kp is with respect to pressure, always measured in atmospheres. And so this would be the partial pressure of SO2 squared times the partial pressure of O2 over the partial pressure of SO3 squared. Any questions? And the reason you might want to do that is if measuring concentrations in pressure was easier than in moles per liter, then this would be an easier thing to do. So Kc and Kp are not necessarily equal to each other, but there is a relationship. And so the partial pressure of a gas in atmospheres isn't the same as its concentration and molarity. It's proportional, but it's not the same. So I think this is, I already did this. I'll do it again. So PV equals nRT, and if we divide both sides by RT, get rid of those, and then divide both sides by V, we end up with N over V is equal to P over RT. And this is molarity. So the molarity is proportional to the partial pressure, but it's not equal. There's a proportionality constant, the temperature, and the ideal gas constant. Any questions about that? So we're going to look at the relationship between Kp and Kc. So the concentration of gas A is equal to its partial pressure divided by RT. So let's look at this generic equation and write out Kc. So that would be, again, products over reactants. So C raised to the C power times D to the D power divided by A to the A power times B to the B power. Well, what if we put this expression, partial pressure over RT, in there instead? Don't worry, I'm not going to make you repeat this. I'm just showing it to you. So the concentration of C would be the partial pressure of C over RT to the C power. D would be the partial pressure of D over RT to the D power, divided by partial pressure of A over RT to the A power times the partial pressure of B, that's not a very good B, over RT to the B power. Everybody okay with that? I just substituted this for the concentration and put the appropriate letters on there. So this is kind of a mess, right? Well, we've got those RTs all over the place, right? So let's pull those out. So this is the same as PC to the C power times 1 over RT to the C power. Everybody okay with that? So I'm going to pull out PC to the C power. What's the best way to do this? Well, let's use negative exponents. RT to the negative C power. So this is equal to PC to the C power times 1 over RT to the C power, right? So instead of having this fraction, I'm going to use a negative exponent here because it makes everything a little easier to look at. So then next would be PD to the D power times RT to the negative D divided by PA to the A power times RT to the negative A times PB to the B power times RT to the negative B. Well, that doesn't look much better, does it? It's okay. Now I'm going to take all my partial pressures and collect those together. So PC, I'm going to get rid of those parentheses. PC to the C, PC to the C, PD to the D over PA, capital A, to the A, PB to the B. Right? It's not confusing at all, 9 o'clock in the morning. Well, this looks a lot like that, doesn't it? Except with pressures instead of concentrations. Well, what happens with the rest of this mess? So if I have something, let's see, if I have x to the A power times x to the B power, that's the same as x to the A plus B. You may not remember that, but it's true. And so I'm going to take these RTs and combine them all together. I've got negative C plus negative D, and then I'm subtracting by this, so that would be plus A, and I'm subtracting by this, so that would be plus B. A plus B minus C minus D. So this comes out to be KP. That's what this part is called, KP, times RT to the delta N. So, no, they do it backwards. I just remembered, instead of doing it this way, they do 1 over RT. So that changes the signs on all of those guys. There's a reason. C plus D minus A minus B. So we call that delta N. Delta N is C plus D minus A plus B. The coefficients of the products minus the coefficients of the reactants. So products minus reactants, final minus initial. Trying to follow patterns here so we can remember which way to do it. And so then typically this is shown as Kp is equal to Kc times RT to the delta N. And I think, yeah, so that's what's on the table of useful information. So this is the relationship between Kp and Kc. This is how I got there. If you followed that, awesome. If you didn't, that's okay as long as you just believe me that it's true, okay? You don't have to understand all the math in there. What does this delta N represent? It represents the difference in numbers of moles of gases. So here we've got products. If they're both gases, we add up the number of moles of gas and we subtract the number of moles of gas that we started with. And that's why Kp and Kc are not always equal to each other, because sometimes you have different numbers of moles of gases and that affects it. Any questions? That's kind of a mess, huh? So there's the pretty one. Delta N is the difference between the number of moles of gaseous products and gaseous reactants. If the total number of moles of gas that you start with and end with is the same, then Kp is equal to Kc. Because we've got Kp is equal to Kc times RT to the delta N. Well, if the moles final is equal to the moles initial, what does delta N end up being? 0. If that's 0, this whole thing becomes 1, and Kp is equal to Kc. So they can be equal, but usually not. Questions? I think the hardest thing about this is remembering what the delta N is. The delta N is final moles of gas minus initial moles of gas. Okay, consider the following reaction, corresponding value of Kc. What's the value of Kp at this temperature? So we're given Kc, they want us to find Kp. So we're going to use the equation we just learned. So how many moles of gas products do we have? 2. So delta N is going to be 2 minus how many moles of gas reactants? 1 plus 1. So that comes out to be 0. Kp equals Kc times RT to the 0, which just equals Kc. So Kp is 6.2 times 10 to the 2. They're not all that easy, sadly. Questions? So what about units? The equilibrium constant. If you put molarities in there or atmospheres for the partial pressures, you would sometimes have units, and sometimes they would cancel out, and the units would be different for different situations. And that's just really messy. And so formally, instead of concentration or partial pressures, what we're looking at is ratios of the concentration to a reference, 1 molar, or ratio of the pressure to a reference, 1 atmosphere. And this makes K have no units, because 3.7 molar, we don't write it this way. Whoops. Got lost. We don't write it this way, but what we mean is 3.7 molar divided by 1 molar. So all the concentrations, molarity over molarity, the molarities cancel out. If you do that with the pressures, the atmospheres cancel out. Yeah. Yeah. So unlike the messy units on the equilibrium constants, the rate constants. Remember, the units got all kinds of messy and different units for different things. We've avoided that by doing this. So as long as we're always using molarity for concentration and atmospheres for partial pressure, we totally ignore units. Okay? Any questions? Okay. Under what circumstances are Kp and Kc equal for this reaction? If A plus B equals C plus D, if the reaction is reversible, or if the equilibrium constant is small. Yeah, it's going to be A. Because if delta N is 0, then Kp equals Kc. And delta N is C plus D minus A plus B. So if these are equal, it'll be 0. Any questions?